Right, okay, in this video we're going to look at some more advanced kind of force problems. This is one I've prepared that just allows us to show you multiple ways of solving triangles of forces and whatnot that can become quite tricky if you haven't enough practice at them. Okay, so you need to have done plenty of practice of these before you can feel confident walking into an exam and trying to tackle one. There are multiple methods of solving them, so I'm going to show you two of the most common methods. The third is the classic scale drawing. So if you've got a ruler and a protractor and you know the sizes of forces, then you can do and angles, you can do scale drawings quite easily to solve these problems. So another nice way of doing it, and all are generally accepted. So let's look at this problem first of all. So what we've got is we've got a box suspended by two cables. One cable exerting a force of 110 newtons, the other cable exerting a force of 152 newtons. So both angles are given with respect to the horizontal, and so we could, if we wanted to, work out the angle between there, and we might have a look at that in a little bit. But as far as to say, what we need to look at now is we need to look at seeing how we can do this problem to make find out what our missing weight is. So in order to solve this problem, what we might start with is trying to create a vector triangle out of what we see. Now, we know from this situation that the horizontal for vectors of these are balanced. This one is balanced with this one. And you could work out what the horizontal vector of this is, and whatever it is on this side, it would have to be on this side, because the forces are balanced. It's not accelerating in either direction, it's not moving at constant speed either, it's stationary. So we would expect the forces horizontally to be equal and opposite. The same thing can be said about the downwards force here. The upward vectors as a result of these two must be equal to the weight in order for it to be held vertically. So we must have a total upward force which will be equal to the downward weight. Okay, and that's going to be our entry point into this. We're going to look to try and see if we can work out what the total upwards vector is. So in order to do that, I can appreciate the fact that the horizontal vectors are cancelled out, and I can create a brand new vector triangle out of all these forces. I'm going to do this down here on the left. So we start with our 110. So we've got our 110 there, and then we're going to add tip to tail, as we do in most vectors, our 152 newtons. And then we can join the dots, essentially. Straighten off. And what we've done when we join those dots there is we've basically come to a triangle that has three sides, and the two vectors are giving rise to a total horizontal component there. Vertical component. And believe it or not, that vertical component there, which actually should be more correctly drawn as that, will be equal to the weight, as we've already suggested. So what else can we tell about this vector triangle? Well, we know that the angle from the horizontal of this vector is 25 degrees. And yes, this is a right angle here, so 90 minus 25, 65 degrees. We could do a similar thing up here. Now we know that the 152 to the horizontal is 49. That means through the geometry of the situation, that angle would be 49 degrees as well. And therefore, because that would be a right angle to the vertical, then we're missing another 41 degrees. So let's have a look where we go from here. So we've got two angles within the triangle. Two angles within the triangle. Don't need that one anymore. I could work out this one. So I've got 65, 41, so that's 106. What's the total angle inside any triangle? Is 180. So I've already said I've got 106, 80, so I've got 74. Okay, so I've got 74 degrees there. Now, why was it important to get that angle and nothing else? Interestingly enough, did anyone see where else I could have gotten that 74 degrees from? Congratulations if you've seen it. You can also just add up those two, and that essentially would be the angle in there as well. So, what we're looking at here is a situation where we've got an angle, and we're going to call this angle A. And those of you who are really hot on your trigonometry, sine and cosine rule will probably know where I'm going with this. That side is A, and we can give these sides letters should we wish. We can call this one B, we can call this one C. We don't need angles capital C and capital B because they're not of interest. We don't need them in the equation for the cosine rule. So the cosine rule is A squared is equal to B squared plus C squared minus 2BC cos A. We just need to throw the numbers into it. So A is going to be equal to the square root of 110 squared plus 152 squared, brackets, minus 2B, I'm going to write in what B is, 110 times 152 times cos of our 74. Bear in mind that square root is over the whole lot. So when we work that out in our calculator, which I'm going to do in a moment, and you should be working this out in your calculator too. Feel free to fast forward me. Right, so I've just double checked my answer twice there in the calculator and I got 161 newtons. So 161 newtons. Okay, with long calculations like that, it's worth just throwing them in twice. If you get the same number twice, brilliant. I do it just as a practice and just to make sure I don't make any mistakes, especially on these videos. So 161 newtons. That is the force, total vertical force upwards, so therefore that is also, as we've suggested, the weight downwards. Okay, so that is the first method of tackling that. Now in the second video, I'm going to show you the second way of tackling this.